All right, kia ora. Welcome to the remote learning for week number 5. This is your first task, and you have a total of 3 tasks this week to work on to keep progressing through our organic chemistry. Today's learning intention is about exploring the alkenes and the alkynes and also looking at their isomers. So that's the first chunk. Second chunk, then, we're going to be looking at the alkene reactions, and that's task 2, and then task 3 will look again at isomers, but in this case, the optical isomers. So by the end of today's lesson, you should be able to name the functional group for the alkene, identify it, draw the structure, talk about its properties, etc., and you should also be able to explain those isomers. I noticed on the success criteria that I forgot to include geometric isomers, and that's something that you learned last year, so I've added it onto this one. So just keep in mind that there's constitutional, which is also known as structural, geometric, and the stereo isomers, enantiomers, optical isomers. That's all in one category. So there's basically 3 different isomers that we are learning. So let's start with the alkenes. Really important thing to note is that the letter has changed, and it's changed from an A to an E. Really important that you're careful with your spelling for organic chemistry, because if you misspell it, you can actually refer to a whole different functional group. This case, the functional group has a double bonded carbon, so the carbon has 2 bonds to the neighboring carbon. Its new general formula then is whatever the number of carbons times 2 for the number of hydrogens. Obviously, we don't have that plus 2 at the end because we removed 2 hydrogens to make the double bond. And these are known as saturated compounds. Some interesting facts. Butter is an unsaturated fat, which is why we call it, it's a saturated fat, and that's why we call butter a saturated fat. And oil is an unsaturated fat, and that's because it has some of those alkene kinks in there. Those kinks mean that it doesn't stack as well. We don't have as many intermolecular forces, and so at room temperature, this is a liquid, whereas butter, having that straight chain, is a solid at room temperature. So I figured that's just kind of cool to see. All right, so with the alkenes, it's a homologous series. You basically have that repeat of the hydrocarbons with a double bond, and the bond angle when we have that double bond is 120. So some physical properties, these guys are nonpolar, which isn't a surprise because it's just carbon and hydrogen. And since they're nonpolar, they won't be soluble in water, but they will be soluble in nonpolar substances. Same patterns that we've seen before. As I increase the mass of my alkene, the melting point and boiling point also increases, and that's because we have now more intermolecular forces. But these tend to be less dense than water, so they will float on top. At room temperature, you'll find ethene, propene, and butene in gases. You obviously don't have methane because you need to have 2 carbons to have a double bond. Anything higher than that is liquids. All right, the next one is the alkynes. Note that this has now changed to a Y. With the alkynes, because we have, again, removed 2 hydrogens, the formula then changes to be twice the number of carbons minus the 2 hydrogens that you've used to make the triple bond. So yeah, the functional group is just carbon with a triple bond. The bond angle is 180. It's straight, if you guys remember some of your Lewis structures. This is also an unsaturated compound because we can break the double bond and add to it. And the same naming rules apply with the alkenes and the alkynes. You change that suffix ending to "ine" instead, or "ein" instead. Cool. So, like I said with the naming, we're just changing the suffix at the end. And again, when it comes to that parent chain, it needs to have the functional group. So make sure when you are numbering that the numbering does include that main chain. If you have a short chain, either 2 or 3, you don't need to state where it is because it can only be in one location. If there's anything more than 4, then you do need to indicate where it is. examples would be but1-ene and but2-ene. Basically, that says but1-ene is that the double bond is between carbon 1 and 2, whereas but2-ene says it's between 2 and 3. But anything with 2 carbon chains, obviously it's between 1 and 2, and if it's a 3 carbon chain, if you flipped it to the other side, it would still be 1 and 2. Cool. When it comes to more complex naming then, you need to first identify the parent chain, figure out where the position of that double or triple bond is, and the numbering now is preferenced to the functional group instead of the branches. So just like with the haloalkanes, the preference always goes to the functional group if a functional group is present. And you want to give it the lowest number possible. After that point, identify if there's any branches and what positions they will be. Remember, when you give them those positions, you only number the chain once, and so it's in reference to the functional group. And then you name the molecule. So branch position, branch name, parent name, double bond position. And again, same rules apply. If you have multiple double bonds or multiple triple bonds, you would use di, tri. Cool. So now I'm going to switch to my document camera and give you some examples of naming and drawing. Cool. So here is opt2-ene. I always draw parent, like main chain first, and then I stick in the double bonds, and then I fill in the hydrogens. So opt tells me 8. 1, 2, 3, 4, 5, 6, 7, 8. Ene tells me there's a triple bond, and that's between carbon 2 and 3. Because remember, whenever we're giving these numbers, it's the lower of the 2. So that tells me it's between carbon 2 and carbon number 3. So if I could go either direction, I either count 1, 2, 3, 4, 5, 6, 7, 8, or I can go this way and count 1 through 8. Doesn't matter so long as I pick one and stick with it. So I'm going to go 1, 2. And I'm going to draw my triple bond over there. I'm obviously not done yet. Do not just stop there on the assessment and go, cool, I've drawn it, because they're going to expect the hydrogens. So again, we're going to go through and think about numbers because we want to make sure every carbon has 4 bonds. In this case, there's 1, so that's going to be 3. This one has 1, 2, 3, 4, it's done. This one has 1, 2, 3, 4, it's done. So there's no actual hydrogens to write there. I'll just draw a line just to indicate that that's the branch. This one, 1, 2, and it's just that same pattern. So that's how we draw that one. All right, here's another example. This one is non-ene. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9. I know that from the non telling me 9. Ene tells me it's a double bond, and the 4 tells me it's between carbon 4 and carbon number 5. So 1, 2, 3, 4, drawing the double bond over here. Doesn't matter, you could have done it the other way. Just like I said, keep to the numbering rule. Right, and then last thing, fill in the hydrogens. So that would be CH3, CH2, CH2. In this case, we have 1, 2, 3. So only one hydrogen there. This case, 1, 2, 3, only one hydrogen there. And then 2 on the rest. And then 3 at the end. Cool. That's what that one looks like. When in doubt, count your hydrogens up, count your oxygens, count your hydrogens, count your carbons, make sure that you have the right ratio. It's a simple way to check. All right, let's get to some more complicated ones. So now we have a branch to deal with. Again, we're dealing with non, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. The ene tells me it's a double bond, and that double bond is between carbon 4 and 5. So 1, 2, 3, 4, 5. So that's where I want to put it. Cool. Now, before I draw in any of the hydrogens, I want to put in that branch first. So looking at that branch, it's a methyl, and it's on carbon number 5. Now, I have numbered it this way, so this is the number pattern I have to keep with. I can't go 1, 2, 3, 4, 5. Actually, it works out the same because 1, 2, 3, 4, 5, it still is on the same carbon. But you should be going based off the number that you've done for the double bond. So 1, 2, 3, 4, 5, I have CH3 that goes there, and then my last step is to put in all of the hydrogens. That one's CH3, CH2, CH2. In this case, 1, 2, 3, only one hydrogen. In this case, 1, 2, 3, 4, no hydrogens there. And then CH2, and then the CH3 at the end. So that's the naming for that guy. Or drawing, I should say, for that guy. All right, moving on then to our next one, which is now we are practicing how to name them. These can get really kind of tricky. You have to be careful in taking your time to find the parent chain, because just because that's the linear doesn't mean that's the chain. You are counting, including kind of the branches coming off. So I notice in this case, there's 1, 2, 3, 4, and 5. So I have some sort of pent. I can see in this case that my double bonds between carbon 2 and 3, but let's check to make sure that is the lower number combination. So that's 1, 2, 3, 4, and 5. So 2 and 3 is the lower number, and I'm going to be using 2 when I go to name this. So this would be pent 2-ene, and that's all you got to do. There are no branches in this case, so keep that in mind. Even though it looks like these guys are coming off as branches, they're not. They're actually part of the parent chain. And don't worry, all these notes will be scanned, so you will have them online. All right, one final example, and then I think we move on to more of the notes, because these, yeah, it's my next section. All right, so again, we're looking for the longest chain. So that's 1, 2, 3, 4. This is a 4 carbon chain. And right now I have 2 as being the option for the alkene. And for the haloalkane, I have the option of 4. Let's just number it the other way and see what I have as options. The other direction, I see that I can give the haloalkanes 1, and my alkene doesn't change. It's still going to be at 2. So I'm actually going to use the orange pathway this time, because it gives me the option of having both the alkene at the lower number and giving the haloalkanes a lower number as well. So since this is a 4 carbon chain, we are doing bute 2-ene. And then now we have these halogens over there, which is our chloros. And I notice there are 2 chloros, and they're on carbon number 1 because we're using that orange pathway. So we'd go 1, 1, dichloro to specify that we have 2 chlorines and they're both on carbon number 1. And that's how you'd name that guy. Cool. Like I said, don't worry, all those will be scanned. Cool. All right, next thing that I then need to talk about as our alkenes is the structural isomers to them and also the geometric. So obviously with structural isomers, you've seen this before, and it's just a change in positioning. So in this case, all these are examples of structural isomers. Bute-1-ene, for example, the double bonds between carbon number 1 or 2, I can move that double bond, and that could be between carbon number 2 and 3. The other option is that I have it as a propene. Now, I don't need to specify where the propene is because it can only be on carbon number 1 and 2. And in this case, instead of having a long chain, I'm now having a methyl coming off of it. You don't need to specify that it is 2-methyl. They have, which is fine, but it can only come off of carbon number 2, because if it was on carbon number 1 or 3, then you're going to go back to the butenes. So that's an example of structural isomers with the alkenes. They all have the same molecular formula, but the double bond and the arrangement of the carbon is different. The other thing to remember about these alkenes is that they can form what is known as a geometric isomer. In this case, we're looking at our structural isomers, but only one of these 2 structural isomers can form geometric isomers. And there's really specific properties that you need to have in order to have those geometric isomers. And that should be an E. See what I'm saying? Watch these typos. Cool. So with these geometric isomers, they have the same structural bonding pattern, but when arranged 3D in space, they are in a different location and thus an isomer. So basically, located in a different location, so geometry speaking, are a different molecule. Now, in order for that to happen, the first requirement is that you have a double bond, and the double bond is really important because you can't rotate with a double bond. And the other thing that needs to happen is that you need to have two different things attached to each of the carbon involved in a double bond. So for the butene, this carbon has a hydrogen and a methyl. This carbon has a hydrogen and a methyl. They don't need to be the same on each carbon. Each carbon needs to have two different things. So if this, for example, had a hydrogen and a chloro, that would still be able to do geometric isomers. The top one here is not an example of something that could do a geometric isomer, and that's because this first carbon here has two hydrogens. So if I flip those two hydrogens around, it's still the same molecule. So that's what you're looking for with these geometric isomers. So let me show you that on the document camera because I do have some models to kind of prove the point. So in this example here, I have a diol, and I say it's a diol because I have two oxygens with that hydrogen, so those are alcohol groups. I have two carbons, and then I have the two hydrogens attached to it. So this would be ethane 1,2-diol is the name for this one. Now, we notice here with this single bond that it can rotate freely around, so it doesn't matter where my molecule is located geometrically because it can move. Now, let's say I remove two of these hydrogens to form a double bond. Bye-bye, hydrogens. And I'm forming a bond between my carbon. There we go. All right, what we'll notice now that we have the double bond is that it's not rotational. And so it matters where the alcohol and the hydrogen are geometrically. So in this case, can't rotate. My alcohols are on the same side of the molecule and the hydrogens are on the same side of the molecule. The only way I can get the other variation is if I physically remove and swap them around. It's really hard to do. Like that. Cool? Cannot rotate, and now I have a different molecule. So this is what I'm saying. Geometrically, they are arranged differently, but they have the exact same molecular formula. They have the same alcohols on carbon 1 and 2, and they have the same double bond in the same location, but geometrically, they're arranged differently in space. And so in this case, my alcohols are on opposite sides, and my hydrogens are on opposite sides. So that's what we're looking at for our geometric isomers. And I just want to make a point that with the alkenes, so we saw an alkane, they rotate, so that's out of it. The alkenes do this, and the alkynes with the triple bond, yes, they don't have that rotational either, but because they only have one thing attached to them on the other side, they don't do geometric isomers, so it doesn't matter. All right, so looking at our geometric isomers, some things to keep in mind is how we annotate which one we are dealing with. And it's just an extra layer to our answers. It just means that if we have the pairings on the same side of the double bond, so hydrogen and hydrogen on this side, that is known as cis. I like to remember them as cis-same. So just write cis and same. Trans, on the other hand, is on opposite sides of the double bond. So the hydrogens you can see on the opposite sides. The way I like to remember it is that you transfer to the other side. And those are your geometric isomers. All right, goodbye. Great work today. I hope this made sense. So today we explored the alkanes and the alkenes, and we looked more at those isomers because you will get an isomer question. End of today, you should be able to talk about the alkene properties, and you should be able to explain another type of isomer. So now just go on to my Google site for your Mahi choice and pick what you want to do. All the resources are on Google Classroom for you.